Okay. Last time we wrote down the Euler-Lagrange equation, and we'll take up from there today. So the equation that I wrote last time was the following. So what we wrote was d over dt, the total time derivative of del t over del q alpha dot minus del t over del q alpha equals q alpha. Equals q alpha. Okay, where T is the kinetic energy, the total kinetic energy of the system. Okay, so you sum up over the kinetic energies of each individual particle of the system, and that's what gives you the total kinetic energy. And because here you have derivatives involved with respect to q alpha and q alpha dot, you clearly have to express your T not in terms of Cartesian coordinates but in terms of generalized coordinates. That's one thing. Okay. Second is you have q alpha on the right, which we wrote down explicitly last time as fi dot del ri over del q, del ri over del q alpha. That's correct. Okay, so let's start from here. Let's assume now that the forces that are present in the which are acting on your system, they are all conservative forces, meaning you can express those forces as the gradient of some scalar potential. Okay, so you can write down a potential energy which will be a function of all the coordinates r1, r2 and so forth, rn. Okay, and you will be able to express the fi's as gradients of them. So that's what we want to write down now. So let's say we have conservative forces operating on the system. Okay, so as I said, I can, if this is the case, then I will be able to assign a potential energy to the system which will be function of all these coordinates. Okay, and then if I want to know the force on the ith particle, then I should take the gradient of the u. Okay, or rather minus gradient of u r1 rn. Okay, because I'm going to write it down several times, I think I would prefer to define u of r. Okay, so by this r I mean the entire set r1, r2, so on and so forth, rn. So the force on the ith particle is the gradient of u. So here you have to take the derivatives, and derivatives with respect to which coordinates? The coordinates of the ith particle. Okay, that is what it is, and explicitly what I mean to say is this. So you take minus del over del xi of u minus del over del yi of u minus del by del zi of u. Okay, that is what is the meaning of this gradient which I have written down here. And we can also write this as our notation which we use as a replacement for gradient sometimes, is I write it down as minus delta u. Again I write r instead of all the r's over delta r I. Okay, that's just a notation. So that's what your forces would be if your system was conservative. Okay, now a simple exercise. Show that q alpha, your generalized force q alpha, is I mean, instead of taking the So here you have gradients or derivatives involved with respect to Ri, and I'm saying that Q alpha can be expressed as del U R over del Q alpha. That's a nice result. Minus. Okay, so you can get the generalized force just by taking the derivative with respect to the respective coordinate alpha, Q alpha. Okay, so let's see. The proof is quite simple. So you have Fi dot del Ri over del Q alpha, and if you sum over all the particles, that is what your Q alpha is, right? Q of alpha. Now because your forces are conservative, I can write down this Fi by substituting this here. So I put minus del U R, or even better, I just do away with the arguments of U. You understand what that is? Minus del U over del Ri dot del Ri over del Q alpha, and you have sum over all of I. And what is that? That's just the derivative, partial derivative of U with respect to Q alpha, because if you do a partial derivative of U with respect to Q alpha, that's what you're going to get, right? You'll run the chain rule, and this is because your U is expressed as functions of R. Okay, so you'll take the partial derivative with respect to R and dot with del Ri over del Q alpha. So that's what is minus delta U over del Q alpha, and this is what we are going to utilize in the next step. So what I'll do is now is take this result which I have just shown and plug it in here. Okay, let's see what will happen if I do that. So I'll have a derivative of U with respect to Q alpha. What I'll do is I'll take to the left hand side and combine with this. This also has a derivative with respect to Q alpha, and this will become T minus U, and you'll be left with a 0 on the right hand side. Okay, so that's what you'll get. So let's see. So I get delta T over delta Q alpha dot, and you had d over dt, minus delta over delta Q alpha, and as I said, I'll bring T, and T was already here. I'll bring the U from the right hand side to the left hand side, and that's what you get. Okay, now before I define, let me say something else. Your U is a function of R's, okay, and your R's are going to be functions of the Q's, the generalized coordinates. Okay, which means when you go from R to Q, your U becomes a function of U of Q alphas, Q's, okay, generalized coordinates. It doesn't become a function of generalized velocities. In this transformation, velocities are not involved from going from R to Q's, okay, which means derivative of U with respect to the generalized velocities is 0, okay, because this transformation from Cartesian to generalized will not bring in the generalized velocities. So what I'm saying is delta U over delta Q alpha dot is 0, which means I can take this 0 and put in here, okay, because I can always add a 0 to the equation and nothing will change. So I can write the above equation as d over dt delta of T minus U over del Q alpha dot. Okay, so because this piece delta U over delta Q alpha dot is 0, I can do this, minus, I bring this here again, delta over delta Q alpha T minus U, this is equal to 0. Okay, let's define this quantity T minus U by L. Okay, this is called the Lagrangian of the system, okay, of the system, because you have summed over all the particles. So L is the difference of kinetic energy of the entire system minus the potential energy of the entire system, and that quantity L is for the system. Okay, so this is called the Lagrangian of the system. of the system. So I can write my Euler-Lagrange equations as del L over del Q alpha dot minus del over del Q alpha L equals 0. Okay, let's see if I can bring in some color. Color puck, I don't know where it is. Okay, never mind. No color for us. Usually people call this as Euler-Lagrange equation, but we will call the previous one also, which had a Q alpha on the right hand side, also as the Euler-Lagrange equation. Okay, that's a nice result. This gives the equations of motion of your system using generalized coordinates. So here you have to express t and u both in terms of generalized coordinates, because the derivatives involved are with respect to the generalized coordinates and velocities. Okay, let's see if I want to say something else here. Okay, what if not all the forces which are acting on the particles are conservative? Let's say you have a situation where some of the forces are conservative and some others are not. Okay, so each particle is acted upon by a force, a part of which is conservative, so you can assign a potential energy, and a part of which is not conservative. Okay, if that is the case, it's clear what we can do. We go back to this equation here, right? That was our starting point, and I split the Q alpha into two parts, one involving only the forces which are conservative, and I bring it to the left as I did just now, so that I define a Lagrangian of the system involving the potential energy, okay, T minus U, and whatever forces are not conservative, I leave them behind on the right hand side. Okay, so your equation in that case would become the following. So if, let's say, conservative and non-conservative forces are present together, or simultaneously, TOGETHER, that's correct. Okay, in that case, as I said, I will take d over dt del T over del Q alpha dot minus del T over del Q alpha equals Q alpha. Okay, and as I said, I will split the forces into two parts and take all the ones which belong, which can be obtained by the gradient of a potential to the left, and I will get d over dt delta L over delta Q alpha dot minus delta T over delta Q alpha equals Q alpha. This Q alpha and that Q alpha are not same. Okay, they are not same. I am not creating a new notation. So here by, or maybe I should, maybe let's say prime. Okay, so here Q primes are due to non-conservative forces. Okay, you can think of various situations in which you will have such a possibility. This is L. Okay, good. So now that we have equations of motion, let's get some very simple examples to get an understanding of how to work with these equations. And the simplest thing you can imagine is always a free particle. So imagine a free particle that's moving freely in space, no forces are acting. And let's see, we get our expected results, that is the Newton's laws, which will say that the acceleration in any of the directions x, y, or z will be 0. Okay, so that's what the example we are going to take now. Okay, let's go to a new page. Example, a free particle. Okay, if the particle is free, then clearly the potential energy involved is 0. Okay, there's only one particle and there are no forces on it. It's free. What's the kinetic energy? Kinetic energy is half m v square, which is x dot square plus y dot square plus z dot square. That's your kinetic energy. And to plug in my equations of motion, I should calculate my Lagrangian first, which is t minus u, which is t in this case. So I take the derivative with respect to the generalized coordinates, which I will take the Cartesian coordinates. Okay, I will take the generalized coordinates to be the Cartesian coordinates in this example. Later we can look at an example where we take some, let's say, spherical coordinates. So what's del L over del X? 0. What is del L over del Y? That's also 0, because there is no x or y here. There are only the velocities. Okay, and del L over del Z, that is also 0. What is del L over del X dot? Del L over del X dot is m x dot, right? So if you take derivative of this, you get mx dot. The derivative of this with respect to x dot is 0. Derivative of this is 0. Okay, these are partial derivatives. Del L over del y dot, again my dot, and del L over del z dot, this is a dot here, is mz dot. Now I take the total time derivative of del L over del X dot, all the three. Okay, so d over dt delta L over delta X dot. So I have to take the total time derivative of this, which will be mx double dot. Okay, and x double dot is the acceleration in the direction x, and similarly you will get, okay, my double dot when you take derivative with respect to the corresponding one here for y, and similarly mz double dot. Okay, so what's your Euler-Lagrange equation? That is d over dt del L over del X dot minus del L over del X equals 0. So this minus this, right? So this piece minus that piece is equal to 0. So I get mx double dot minus 0, because this is 0, is equal to 0. My double dot equals 0, mz double dot equals 0. So we get our Newton's equations for free particle, which is what we should expect. Now imagine if the particle was not free. Okay, let's say it was acted upon by a force. Okay, let me do it here itself. Let's say there is a force F. So let me not invoke potential right now. Let me just work with the generalized forces. So my generalized force Q x would be Fi dot, remember what that would be, delta R over delta X. Okay, remember Fi dot delta R over delta Qi. Now Qi is X here, and I should sum over all the particles, but there is only one particle, so this is what it is. And what is this? F dot delta R over delta X. So what is your R? R, vector R is the position vector, right? So the S component of it is X. So delta X over X is the unit vector in X direction. So it's, let's say, X hat, which is Fx. Is it clear? So delta, so let's say R is X, Y, Z, right? So if I take the derivative of r with respect to x, okay, this is what you are going to get. You are going to get 1, 0, 0. So that's what I'm doing. I'm dotting the f with 1, 0, 0, and I get fx. Similarly, your qy would be fy, and your qz would be f of z. Okay. Now you see the equations of motion in this case would be, remember your equation of motion when you write in terms of generalized forces does not have Lagrangian on the left but has t on the left. Okay, the derivatives of t with respect to the q and q dot. So your d over dt of delta t over delta q dot minus d over dt, sorry, dt over del q is q, and I should write alpha, right? Remember this. So from here you get easily mx double dot, right? This will give you mx double dot, the left hand side, which we saw above, and the generalized force is the x component. Okay, or if you combine all the three equations and write them in the vector form, you get, okay, which is your expected Newton's second law. That is okay, that's good. Maybe I'll take up 2 more examples in the next video, and we'll stop here. Let me see if I want to say anything else. Yeah, maybe I can make that comment here itself. Let's go to this place. This does Euler-Lagrange equation. Now you see, this is very nice. Imagine you have a set of particles. Okay, let's say your system is isolated from everything else, and there are a number of particles in there, and they are interacting with each other with whatever interacting forces they have. Okay, whatever constraints are there. Now to know what or how the system is going to evolve with time, okay, you don't need to track, you don't need to know all the forces that are acting on each particle. Okay, that's what you would have used if you were doing using Newton's equations. But here you don't have to. What here you have to do is you have to know a quantity L, the Lagrangian, which knows about the entire system. Okay, L is for the system. So once you know the L, you can derive the equations of motion, and you can describe the trajectory with time. So L is a piece, is a very central, very important part of the subject, and you are always after finding the L. In fact, later you will see that when you start doing, let's say, looking at the fundamental forces and try to make quantum theory of nature, you start trying to guess what the Lagrangian could be. Okay, from whatever data is available to you, you start guessing it. You start make certain assumptions that the Lagrangian has to be this form. Okay, and there are you impose certain symmetries that you know. You remember we have already talked about this some symmetries in the very first video, first or second, I don't remember, and that put constraints on what kind of what could be the nature of forces. Okay, so similar constraints you can apply on the Lagrangian itself. Okay, and that's what the strategy is when people are working in, for example, high energy physics. Anyhow, that's all for now, and we'll take a few more examples in the next video. See you. Bye.